This is going to be a little demo of the Welsh's version of the t-test that we use in situations of unequal variances. First off, let's just review a couple of the key points about the regular independent samples t-test, also called the student's t-test. And we use that test normally when we meet the assumptions for the statistical test. I'm still using the same problem, comparing test anxiety in students who attend a prayer ceremony with students who participate in a late night study session. Here are the parameters of what we're testing. When we have equal variances assumed, which we do in this case, you can even see here, even though I've changed the data a little, you can see that we meet the 4-to-1 ratio, and this did pass the Levine's test of equality of variances, so we can use this test. One thing to remember is, first off, a change that we'll see in the Welch's is how we calculate DF total. In the student's t-test, we simply add DF1 plus DF2. And that's how we get the total. We're going to do it differently in the Welsh's t-test. The second thing to remember is that when we calculate the estimated variance, we actually pool it to calculate pooled variance by multiplying the variance times the proportion here. And that's how we get our pooled variance. The proportional representation of each variance. When we do the Welsh's t-test, you'll see that we are not going to use the pooled variance. So those are the two differences between these test types. Let's look at the unequal variances. Excuse me. So the example that we have here, once again, is not the example I used when testing the assumptions because I wanted to illustrate a different point by changing the data slightly. But I do have an example here of test data that has unequal variances. You can see that we parse the problem in the same way. And actually, every single step is the same. But what will be different is the way we calculate spread and the way and the cutoff point that is determined because our degrees of freedom will be different. Let's go ahead and run the test. We can see our data here, and I started the calculations by putting in N and DF. We calculate the average in the same way, and we do it for both sides, but I'll do it one at a time. We calculate the deviations in the same way. We take each score and subtract the mean. I'm going to add the $sign in here. And so here we go. And we add the $sign to hold static at this cell. Every time you do a copy paste of any formula in Excel, you should check. I can see here that when I click on student 5, we do have the correct score. The student's 32, subtracting the mean. So these should be just fine. Let's square the deviations. And pull those down as well. We can now get the sum of squared deviations. And estimate the variance. And I'll just remind you of some of these formulas. The estimated variance is SS divided by DF. And so let's go ahead and get that equals SS divided by DF. And we'll end up doing both calculations the same for both sides. I'm going to take the next step then and calculate var, which is equals E var divided by N. That's how we take care of the sample size, and that's as far as we'll go. Now, because I've taken care with how I line up these data, I can use copy paste for these functions. So I'm just going to copy and paste, and then as always, I'm going to check that the calculations were done right. I have to throw these in there as well. You can't do this unless you take great care, because if you do it carelessly, your lines will be off and it'll show up. For example, look what I did here when I copy pasted. I accidentally added a student. If we were going to calculate and accidentally included that row, all our numbers would be off. another caution about why we have to be very careful when copy pasting. I'm going to take care and make sure that I lined up the formulas properly. This one does look like it's subtracting correctly. And I do have the correct number for the squares, and that also appears correct. I'll just verify that the sum of squares is adding the correct column, and it is. And so we should be good from this point on. I'll check that varm divided by n. All right, so we should be set here. So here is where we diverge in the two tests. First of all, you'll notice that we went right from evar to varm without using a pooled variance. That's because of those unequal variances. It doesn't work the same. We can't use those proportional numbers. So we'll go ahead and calculate the rest of this problem and then take a look at it. So let's take mean, I think mean 1 minus mean 2, actually. Mean 1 minus mean 2. Doesn't matter which way you go on this. The only difference will be in the signage. Varm, we calculate the same way we did before by summing up the varm 1 and varm 2. And we take the square root of that to get our spread. And so now we know that the shape of our distribution is normal T. And the center is 0, meaning two distributions that have no difference in their means. And our spread will be SM equals 2.6371 or 2.6372. All right. Our cutoff point we have to look up, and to do that, we need to know degrees of freedom. So let's look at a little segment of a new formula. So the total formula involves a little field we're going to call df denominator. Df denominator is just varm1 squared divided by df1 plus varm2 squared divided by df2. I now have my gloves so I can write that down. So df denominator, I'm just going to call it df den 1 equals varm1 squared, put the little caret there too, divided by df1, and df denominator 2 equals varm2 squared divided by df2. So let's get those formulas in. Equals varm1 squared divided by df1. And df denominator 2 equals varm2 squared divided by df2. We sum these up to get the denominator for our formula, but the full formula is actually varm squared divided by df denominator 1 plus df denominator 2. So let's go ahead and get that formula in. Equals varm squared divided by df denominator, let's put a parenthesis here, df denominator 1 plus df denominator 2 and close the parenthesis. So take a look at the formula once again. We're taking the varm1 and dividing it by the sum of these two df denominators. And I'll double check and make sure I did all of these formulas right. This does look like what we have. So notice what our degrees of freedom is. It's 9.87. If we had a normal calculation for degrees of freedom, it would be 15. So this does make a difference. So let's hold this thought for just a minute here. Let's calculate our t-score, which you'll remember t is just m1 minus m2 divided by SM equals, here's m1 minus m2, I'll just grab that, divided by SM. And you can see we get a t-score of minus 1.701121. So before we do anything else, let's see what this means in terms of our statistical test. Let's find out our cutoff point. Cutoff point for 9.87. Let's get our tool out. 0.05, and let's get 9.87. And we find that our cutoff point for a left tail test is minus 1.81. So let's put that in here, minus 1.81. And we can draw it into our distribution here, minus 1.81. That can be helpful. And we can shade the tail just by way of remembering what we're doing. Okay. And with this information, we know that our sample score of minus 1.70 is in the fail region, right around here. TS equals minus 1.70. We know that that leads us to, I'll just click on this right here. And we know that leads us to fail to reject HO and conclude a non-significant result. Students who attend the prayer session do not have significantly lower test anxiety than students who attend the late night study session. And I'll just put the statistic down here. T, we still write it the same way. We write our degrees of freedom. I'm just going to round to 10 equals minus 1.70. And we just write not NS, not significant. So you can see where this difference was. It fell in two areas. It fell in our degrees of freedom, which ended up giving us a lower cutoff point, and it fell within our calculation of our variance. Let's look at what difference it would make if we had done the regular test without doing this adaptation for the unequal variances. I'm going to copy these data and just paste it into this where the test has already been completed. And let's see what results we get. So when we get this different result, you'll see that first off, we get a higher t-score of minus 1.76. Secondly, we get a different cutoff point. Let's enter this as 15. So once again, our left tail was minus 1.81. Now let's enter the 15 and calculate. And we get a cutoff point of minus 1.75. And we can see here that with a cutoff of minus 1.75 and an actual sample score of 1.76, TA equals 1.76. And here we had all of this area in the reject region. Let me do this just a little more neatly here to show the point a little better. Sorry about that time consumption here. Our new cutoff point was 1.75. TA equals minus 1.75. We knew that our shaded reject region was all here. And we knew that our sample score was minus 1.76, which is in fact in the reject region. I think my pen might be going dead on me. TS equals 1.76. And so you could see that we get an entirely different outcome from these two tests. In one situation, we can reject the null, and in the other situation, we can't. And that's why we have to be careful with these tests. You might be wondering how we go about calculating the effect size. And the effect size is just the same as before, except I'll give you an easier way to do it. It's just M1 minus M2 divided by, let me scroll just a little here, divided by the square root of the average EVAR 1, EVAR 2. And so let's go ahead and do that. What that really means is that S is calculated by equals the square root of EVAR 1 and EVAR 2, square root of the average, sorry about that, average of EVAR 1 and EVAR 2. I'll show you the formula again in a minute. So here it is. The square root of those averages, that's going to be our standard deviation for the distribution of individuals, 5.33, bigger than the standard deviation for the distribution of means, as we would expect. And for our ES, we just take our M1 minus M2 and divide by that new calculation of S. And there we get our minus 0.84, a large effect size, but we couldn't reject the null. And so that's that kind of fluky thing that happens when you have oddly distributed data. So once again, this was the Welsh's t-test that you use in the situations of unequal variances.